get started. So welcome everyone. So this is the international webinar series on geoenvironmental engineering, sustainability, and resiliency. So my name is Krishna Reddy. I'm at University of Illinois, Chicago. I'm the organizer of these webinars. And these are weekly webinars covering wide range of topics related to geoenvironmental engineering, sustainability, and resiliency. And mainly, the purpose of these webinars is for you to recognize emerging challenges, exploring innovative solutions, and more importantly, fostering collaborations. So it's not restricted to anybody. Anybody who is interested can attend it. And there is a registration link, to use it to register and get the link to join. So luckily, we have several webinars recorded. They are available on YouTube channel. I hope you got a chance to see them and inform your students about those. And so this schedule for this spring is excellent. I'm looking forward to learning a lot of stuff from these webinars. So I hope you have the entire schedule for this spring semester. Um, so for this webinar, as of this morning, we have 362 registrations. So I request everyone to switch off your mic and switch off your video. And at the end, you can show your video and make a comment or ask a question. And if you need a certificate of attendance, there will be a Google form distributed towards the end of the webinar. So make sure you sign up that one. You must attend the entire webinar in order to get the certificate. So we keep track of the attendance time using the Zoom record. So if you need PDH hours, you just make sure you indicate that one. There may be some nominal fee associated with that one. So I'm very excited about today's topic and presenter. Today's topic is an overview of life cycle assessment related to use of recycled materials in highway construction. If you want to think about somebody who has done this work, Professor Edil Tuncer comes to mind. He has done this work. This is very hot topic now, but he has been doing this one for many years. Professor Tuncer is Emeritus Professor in the Department of Civil and Environmental Engineering at University of Wisconsin-Madison. He was also the Director of Recycled Materials Resource Center, and he was also Director of the Wisconsin Highway Research Program. He received his bachelor's and master's in civil engineering from Robert College in Turkey. He did a PhD in civil engineering from Northwestern University here in the US. His research expertise is very broad. He works on many different topics in geotechnical as well as geoenvironmental. So he works on soils, behavior of soils and waste. Particularly, he has done a lot of work on peats and organic soils. He works on industrial byproducts and recycled materials. He works on geosynthetics and their applications. He works on conventional geotechnical topics like piles and anchors. And he's also, has done a lot of work on coastal erosion and slope stability. He advised many PhD students. He has published more than 400 excellent publications. And he received many prestigious awards, including the ASCE Distinguished Membership, ASCE Carl Terzaghi Award, ASCE Wisconsin Section Distinguished Service Award, and many awards for his participation in ASTM committees. He is very active, and he has developed many standards. So with that brief introduction, I want to thank Professor Edil Tuncer in advance for agreeing to give this presentation. And I want to thank all of you for joining this webinar. So let's listen to Professor Tuncer and learn from his experiences on use of recycled materials in highway construction and how you do the sustainability assessment using LCA. Thank you so much, Professor Tuncer.
Thank you, Krishna, for this wonderful introduction. As you mentioned, I worked on different things and so forth, but also in geoenvironmental engineering, which I've been involved since the start of the field. I was involved in different topics. I consider my work on transport of volatile organic compounds from clay and geosynthetic miners is my major contribution in that field.
Yes.
But last so many years, I got involved with transportation systems, highways, and again, many aspects of it. And the life cycle assessment relative to use of recycled materials in highway construction became an issue. As you know, we moved to modern times. Sustainability became important, but also the measure of sustainability came to forefront. So let's get started. This is our current life. Look at the transportation system on the upper left and lower right, and look at our cities. And this sort of growth is not necessarily sustainable. And the word sustainable is very popular. Everybody uses it. But sustainability is not climate change. It's not environmental science. It's not energy conservation. It's not greenhouse gases. It's not the go green concept. However, it does touch upon every one of these things, and it is more than any one of these things. So what is sustainability? It is managing the society today in a manner that does not compromise the quality of life and opportunity for future generations. It's a very broad definition. When we talk about environment, all parts of Earth that we live on is environment: air, water, soil, rock. And sustainability requires a holistic approach in which we pay attention to environmental issues. Of course, we have to deal with economic issues and social aspects. This is not all that well developed in our approach, but at least it should be recognized. And these three together is called triple bottom line. So if we look at this figure, there is a circle which has the environmental aspects, yellow circle, red circle, social, and blue circle, economic. And when we are doing a design as engineers, we are trained to make sure that it is an economic design. That's the main motivation of all design. We try to optimize economics of a given project. But more and more, we are also paying attention to environmental impacts and to a certain extent, social aspects. The sweet spot in the middle is where economic, social, and environmental all come together, but that's sometimes hard to find. What motivates sustainability or paying attention to sustainability is primarily the significant growth in world population, which is accelerating. If you look at the numbers, for instance, it used to take 35 years to have a 1 billion increase in population. Then it is cut down to 14 years. And and as shown in the graph, starting from the Old Stone Age, there's a very significant growth in population. And this map shows the United Nations metric on quality of life. And as you see, it's not even throughout the world. The dark green, which is primarily North America, Western Europe, and Australia, have very high numbers. And there are some areas, Eastern Europe and some in South America and so forth, are lighter green. And the medium, which is yellow, covers very large areas, for instance, of Asia and of South America and part of Africa. And then finally, there is the red area, which has low human development factor, and that is mostly in Africa. So we have what is this metric? This metric depends on life expectancy, education, and the income of these countries. And as you see from that, there's first of all an unevenness throughout the world. A colleague of us in the University of Wisconsin showed this relationship where the Human Development Index that depends on health, education, and living standard increases, and there's a good correlation between that and the use of energy. And the countries that use more and more energy also have high Human Development Index.
Tuncer, you are muted.
Hi,
Yeah.
back again.
Yeah, and you know,
Something
keep
here
and
which
yeah,
kind of,
also put it in the presentation mode. I think that's the
yeah.
some screen came.
Anyways, move on.
Yeah.
There is a rapid economic growth throughout the world, and but also there's an increase in global population. And there are constraints on available energy, and there's an increasing emissions and impacts on the environment, for instance, global warming. And the resource availability is also an issue. Availability of water, metals, cement, oil, etc. World population is currently 7 billion. And by 2100, it is projected to be 12 billion. United States is at 0.4 billion, 400 million population by 2050. If you put US and European Union, and that's the dark green areas on the map, their combined population is 250 million. In terms of consuming the world resources, they are number one, this group of countries. China, India are coming fast and will be dominant in the next 20 years. And by 2030, US, which is the largest economy in the world, will become the third largest economy. So we have 7 billion people, and 0.75 billion are in these Western countries. But there is the remaining 6 billion, 6.25 billion. They also want to have everything that we have in the West. And but this is not possible with so just a second. And there are not enough resources to have the remaining people have the same level of quality of life, not just enough things. So we have to make things sustainable. As part of that, we are civil engineers mostly. Infrastructure construction need also to be made more sustainable. So how do we do that? Well, we have to reduce energy consumed in construction, rehabilitation, and use of infrastructure. We have to reduce emissions emitted during construction, rehabilitation, and use. And we have to reduce consumption of natural resources during construction. And there is one other thing which we can do as engineers is that we can increase the service life of the infrastructure we build. That'll provide savings in all these 3 areas that I just mentioned. Using recycled materials is one strategy to promote construction sustainability. Why? First, it avoids energy and emissions associated with the mining and processing construction materials. Energy has been already expended in the first life of recycled materials. 2, it avoids use of natural resources. And in civil construction, sand, gravel, limestone, oil, etc. And 3, it may increase service life, which may come surprising to you, as you would think that recycled materials are inferior to the natural materials, but that's not true. By smart use of them, you can increase service life, thus have savings. So we shouldn't look at infrastructure as a landfill, where you put recycled materials and so forth, but as a place where we have better and longer lasting infrastructure. What are some high volume industrial byproducts in North America, for instance? Coal combustion products, fly ash, bottom ash, boiler slag, and scrubber sludges. These are abundant and not always used beneficially, often disposed in landfills and ponds. Iron foundry byproducts, molding sands in casting, metal casting, slags. Demolition materials, concrete and asphalt. For instance, highways, we replace them and we remove concrete and asphalt, paving, creating huge amounts of demolition materials. Same way, there is a renewal of buildings, which is very critical. And earthquakes, for instance, in Turkey here, they have to demolish large numbers of buildings because they are not safe enough and replace it, which means they'll create huge amounts of demolition, debris such as concrete and so forth, on one hand. On the other hand, they will be trying to use more and more natural resources. Wood and pulp, paper mill residuals, rubber and scrap tires, and asphalt roofing shingles. I worked on all these things. I know Krishna also worked on rubber and scrap tires in his early days, and these are abundant, and we're looking for ways of using them. These are the pictures of some of these materials. For instance, lowest middle material is essentially Class C fly ash, and lowest left is tire chips, and there are some recycled asphalt pavement and concrete type of materials. So these are all various materials, and as you can see, many of them are granular materials, and we know from soil mechanics, granular materials are stronger than cohesive materials. And then we also know some of these things are binders, such as fly ash, which also creates a strong material. So our approach has been in Recycled Materials Resource Center, and we've had that center for like 20 years, and promoting use of recycled materials in construction, primarily highway construction, where large quantities of materials are used. We promoted two principles: wise use and safe use. Wise use is that you just can't take any recycled material and try to use it. It has to be suitable for the infrastructure, for the environment, and you have to provide procedures for appropriate use. Safe use is, well, these materials, it's not like sand and gravel, tested for centuries, used for centuries. They are new materials, and there's always some question about what would leach out of them and whether it could have any adverse impact on environment. So we have to check both of these things anytime we propose a recycled material for a specific use. For instance, to check WISE, you have to run tests. For highway applications, you need resilient modulus. So you have to know their resilient modulus and see if it is enough to provide a WISE application. You have to evaluate their safe application. In other words, you have to look at whether it will adversely affect environment, usually water. And you have to look at the leaching potential. Here's where the geoenvironmental engineering comes to picture. There are various methods of studying the leaching characteristics of these things appropriate for the typical environments that they are exposed to. I'll just make one little comment here. For instance, take rubber or tire chips. If you do a chemical analysis, you'll find there are all kinds of horrible things in the material. And you will say, oh, no, we can't use this thing or anything because of these toxic materials that are present in it. However, they do not leach very easily because of the composition of the tires. And this took a lot of effort to explain, as you know, crumb rubber is used in artificial turf construction, and the people were very concerned about it at one point. But now they understand that it doesn't leach these toxic things in a substantial quantity. There's a new EPA methodology called Leaching Environmental Assessment Framework, which studies the leaching characteristics, function of pH, and this is a new protocol available that we use. Now let's come back to evaluating sustainability. Saying something is sustainable is not very useful. We have to have quantitative measures of sustainability. There are a couple of things come to picture here. One of them is life cycle assessment, LCA. It computes the sustainability metrics. For instance, what is involved in terms of energy, greenhouse gas emissions, water use, hazardous waste generation, etc. This is sometimes called pollution counting. And we are now have the ability to make this sort of assessment for new applications and so forth. Another thing we have to look at is life cycle cost analysis, LCCA. Now, this is the significance of this is it doesn't focus on initial cost of something, but rather the life cycle cost. And when you are evaluating different design alternatives, you have to look at the life cycle of them. Something which is cheap but doesn't last much, and or difficult to dispose at the end of its life and so forth, may not be as desirable. So you have to do a life cycle cost analysis. For highways and so forth, these things are widely developed. Quantitative and auditable metrics are needed. Provide perception and financial incentives for owners and contractors to incorporate sustainability principles in design. Anyways, the summary remarks I have is that incorporating sustainability into design can create significant value. You can have physically superior, economically superior, and attractive designs, which is more than go green. Incorporating sustainability requires rethinking approach, different materials, different methods, different conceptual models. For instance, in use of recycled materials in highway construction, highway engineers are not experienced with recycled concrete, recycled asphalt, and a few other things. And they don't dare to use because they don't know if they are wise or safe. So we've been working hard to provide standards, specifications, and so forth, test and characterize these materials. Being quantitative is essential. Seeming to be sustainable may not promote sustainability. I think to use this such and such thing is sustainable doesn't go far. You have to use life cycle assessment tools to show how sustainable it is and to see what target of sustainability you are achieving. Evidence across industry sectors demonstrates that incorporating sustainability strategy has lasting and economic benefits over performing conventional operations. So we shouldn't approach this as another, headache, but rather approach this as something advantageous. For instance, for highway construction, we build a program called Building Environmentally and Economically Sustainable Transportation Infrastructure, highways, so called Best in Highways. It is based on two things. One of them is a program called Palate, and this is developed by our Recycled Material Resource Center. It allows you to calculate energy, carbon dioxide emissions, water use for mining and production of various materials, their transportation at the project site, and the placement. So in all these different aspects, how much energy is used, how much carbon dioxide emissions are generated can be calculated. You can do this with Palate for natural materials, sand, gravel, etc., asphalt. But you can also do it for recycled materials. The second element of best in highways is the service life determination, and it is based on International Roughness Index. And that tells you how many years of service life we can expect. The program looks like this, and it used to be on our website. Our contract ended about a year ago, so I'm not sure what you can find at the website, but these are all in public domain. Now the Recycled Materials Resource Center is being reactivated with the sponsorship of Iowa State DOT and Michigan State University. But anyways, Best in Highways requires project information, service life estimation. There are weighing options for different factors, and then performance indicators. It allows to do a life cycle assessment and life cycle cost analysis, and also gives you a handle on traffic noise, stormwater management, and recycling ratio. So you obtain all this information in that. The way this program is made is like this, the circle at the bottom. After discussion with stakeholders, we came up with targets, and the targets include like 20% reduction in energy use, 20% reduction in greenhouse gases, and 10% life cycle cost, 10% reduction in hazardous waste generation, 10% less, and water consumption, 10% reduction, material reuse, recycle, 20%. So if you achieve these target values, then you can rank your project, and this shows how these things fit together. And there are programs used for certain technical things. For instance, performance matrix, you see International Roughness Index, life cycle assessment, life cycle cost analysis, etc. Here is a summary of criteria and targets in Best in Highways. So again, based on discussions with our shareholders, these are the targets for environment and for economic. And if we meet these targets, for instance, if we have a 20% reduction in greenhouse gas emissions, that translates to 1.3 billion tons of carbon dioxide in 50 years, and so forth. And so the structural Best in Highways is like this. First of all, there is the mandatory screening layer. If there are certain regulatory requirements, project-specific requirements, you have to take care of them at the beginning, and then you go to judgment layer. You look at the environmental indicators, economic indicators, and possibly social indicators. And at the end, if you achieve 90%, then you have a gold ranking for that highway, and 50% bronze, that sort of thing. Some of the features, there are weighing options for, is the energy more important or the greenhouse gas emissions more important? So there are weighing factors to deal with those. Prediction of service life, performance simulation with Polite, And for the cost, there's a program called Real Cost by the Federal Highway Administration. And at the end, there is a score summary and labeling and so forth. Okay, so this is the end of my general remarks of life cycle assessment. I'll just give two examples to close it. Here is two pavement designs, and one of them is a reference design on the left, and the other one is the alternative design, which uses recycled materials. And they are not, for instance, at the top, there is 160 millimeters of hot mixed asphalt. And we kept that the same in this particular example. However, there are things you can do with asphalt. You can, for instance, mix recycled pavement materials in asphalt mix. You can put roofing shingles, which contains asphalt. And so you could have some recycled materials there. But our primary focus was on the base course. Typically, you have crushed aggregate base course. And we said, how about we take recycled pavement material and add 15% fly ash and make that our base course. Actually, this option would give a much stronger one than crushed aggregate base course. And then there is a sub-base. Usually it is like a sand material. And we are saying, how about if we use foundry sands? For instance, in Wisconsin, there are many foundries, metal casting foundries, steel, aluminum, and so forth. And they use sand mixed with a little bentonite in making the forms. And it is wasted after a while. And so that's what we are talking about. Finally, the subgrade. Now, when life cycle analysis is made, looking at the environmental metrics of carbon dioxide emissions, energy, hazardous waste generation, and water consumption, conventional materials and recycled materials are listed. There is the material production, there is the transportation of these materials to the construction site, and the effort of construction, spreading the material, compacting it, and so forth. And for each one of them, the quantities are given. But if you take the differences in the last column, you'll see there's a 20% reduction in carbon dioxide emissions. There is 16% reduction in energy consumption and 6% in hazardous waste reduction and 11% in water use. For instance, this particular example, we don't meet the 20% target of energy reduction, so it will not qualify for the gold ranking. Some of you may know for buildings, they have this sort of ratings, gold, platinum, gold, and silver, and so forth. So that's what we are trying to emulate here for highway construction. There is also a life cycle cost analysis for this example. And as you can see, there are different costs, agents cost, user cost, and the total. As you can see, there is like 21% savings in cost. This last example I'm going to give before closing is greenhouse gas impacts of harvesting coal ash for cement replacement in concrete. This is a project we just completed at University of Wisconsin. And here I'll just only talk about greenhouse gas emissions. You may or may not know, and those of you in India and so forth probably know, in the United States, where power plants are switching from coal combustion to natural gas. And when they do that, they do not produce fly ash or bottom ash. And these are byproducts of power generation. And for many years, people were looking, how can we get rid of these materials? And only maybe 40% of them were used beneficially used. But now in some states, we have a shortage of these materials because of their switching to gas production, natural gas power plants, as well as increasing renewable energy sources and so forth. And so as a result, and then there is also concern about the old materials that were disposed, especially in impoundments. And you know what happened in Tennessee, fly ash impoundment broke and caused a lot of environmental damage. So EPA doesn't want these impoundments anymore. They need to be removed. And so what do? You harvest this material, and there are two options. You either go and put it in a landfill, or you beneficiate and use it in construction. Where do we use it in construction? Well, yeah, fly ash can be used to stabilize base cores or subgrade and so forth, but the largest use and the most effective use is replacement of Portland cement in concrete production. And fly ash, first of all, improves the properties of concrete on one hand. On the other hand, it saves you use of Portland cement, which has huge amount of greenhouse gases generated during its kiln production. And so for those reasons, people like to use different percentages of fly ash, and 20, 30, 40% sometimes. And it gives you a different strength concrete. So we evaluated the effect of fly ash in beneficial use in concrete and so forth years ago. But now, Electric Power Research Institute asked us to evaluate and compare the harvested coal ash in these terms. Processing pathways for generating a C618 fly ash. This is the ASTM designation for the fly ash. And if you have that fly ash, you can mix it with Portland cement in concrete production. On the left, we have fresh coal ash, and on the right, harvested coal ash. And you see fresh coal ash with very little processing, whereas harvested fly ash, you have to excavate it, dry it, and adjust the particle size and carbon treatment, remove the carbon. And this is a little more complicated, but I want to show you all the things
can you
involved.
close that message you got?
What
You got a message on your screen. Just close that one. There's a message. There's a reminder.
Oh,
A
this thing
reminder
is
you got
showing.
it. Yeah, it's showing up on the
Yeah.
slide. So yeah, just yeah.
How about that?
Yeah,
Thank you.
yeah, perfect. It's good now. Yeah, it's good.
Okay. Yeah, so you see in the harvested coal ash, there's all these different activities, drying, particle size, but more importantly, carbon treatment. These things come with a certain amount of carbon, which is detrimental to concrete production, and you have to reduce that. And you can do it thermally, you can do it chemically, or you can do electrostatic. So we looked at all these processes and talked to the people who does this in the field and generated the information, how much energy it takes to do any one of these things, and how much greenhouse gases are generated. So this picture shows you the greenhouse gas generation per ton of this fly ash produced. And at the bottom, you see fresh, landfill, impoundment. There's the source of fly ash. As you can see with fresh, there's hardly much of anything, but landfill, a little less, impoundment, a little more things involved because of the high water content. And then there is a grinding and then the carbon treatment, which involves screening and grinding and then doing chemical and electrostatic and thermal type of effort. This shows, in summary, on the left, you have the fresh fly ash just from the power plant with very little treatment. And these columns show, there is the life cycle of the production of this harvested fly ash, but then you mix it with the Portland cement, different amounts, nothing, 20%, 30%, up to 40%. And depending, more you put, of course, you have better results. But anyways, let's take a look at the fresh ash on the left. And with more and more incorporated into concrete, you have less and less gas emissions because of Portland cement. The amount of Portland cement is reduced. Same way for harvested ash with different treatments, thermal, electrostatic, and chemical treatments, and so forth. But in summary, using fresh or harvested ash as a supplementary cementitious material that replaces a portion of the Portland cement in concrete has a net environmental benefit with regards to greenhouse gas emissions. Carbon treatment technologies can have a significant impact on environmental benefits of using harvested ash to replace cement in concrete. The impacts increase with increased processing. Harvesting impacts come mainly from drying, with the exception of water. Processing of ash from impoundments versus landfills is comparable due to many of the processes being common, like excavation and so forth. But overall, the fly ash harvested from landfill that was disposed in a landfill and now harvested from landfill has less impact. Okay, I think I am at the end here. And there are some unresolved issues with some of the recycled materials. For instance, high pH and clogging potential of recycled concrete aggregate is a problem. Thermal sensitivity of RAP, it creeps and there's more permanent deformations in hot climates. Leaching and high pH of fly ash and effects of RAP, RAS, and ground tire